So I think so this is the analog of this of the computation of the oscillating integrals in terms of Feynman diagrams. This is the Grassmann analog of this. And now you can imagine that. So let me. Yes, you can imagine that there is a situation when you have both these Grassmann variables and usual commutative variables. So this is the situation when you have so-called super manifolds, and basically it's the following. So super manifold M N M should be considered in terms of functions on the on this manifold. So, and the totals, the manifold itself, it's something like this. So you have a these are sections of the vector bundle P over Mn, where the fiber is the exterior power of Cm, the exterior algebra of Cm. So so this is the even part, this is the manifold.
Strictly speaking, it's
The
only
even part
locally true. If you can you have any coordinate pattern, simple coordinate pattern on Mn, this is true. But if you change coordinate pattern, in general, this vibration structure is possible. But it's just.
I think well.
You can have transition functions which involve.
Which makes both
the coordinates of Mn and even variables in the fiber.
You know, let's not. Yes, it's completely correct. So let's just consider the case when it's a trivial one.
Okay.
That's really correct. So in terms of.
No, please don't. It looks like you rubbed out what you're going to repeat again.
Yes, so it's just a tensor product. It's just a tensor product of the functions of M and the exterior algebra of Cm. So now how to integrate over such thing? Well, let's assume that M has the volume form dx. So then, when we have an element of this space, the integral over M and M is the following. First, you take the top part of M in this exterior algebra, and then you integrate it over dx. Oops. So this is what is called, it's the definition of M and M, f of x, c, dx, dc, where I assume that c1, cn are elements of this Grassmann, generators of this Grassmann algebra. So now, without going into details, just since we did both the case of usual manifolds and the case of Grassmann algebra, so just make this statement without proving it. If we have a function on the supermanifold M and M, So what is the function from such a manifold? Again, it's n0 x plus f x ci plus and so on. So here we have fi1 fik x ci1 cik, and I'll put here 1 over k factorial plus 1 over n factorial m factorial. So there will be no factorial. I'll just write it like this. So but this is of course 1 over n factorial. Same thing. So the statement is that it is asymptotically equivalent to
f of x comma c.
f of x comma c. Thank you. 2 pi h to the power n over 2, then the factor h to the minus n over 2, sum over a. These are critical points of 0 of x. 1 over the square root of the determinant b of a e to the I f0 a plus I pi over 2 the signature b of a, and b of a is maybe I should use, sorry, I want to use here the other indices, maybe alpha and beta. Just to distinguish with the coordinates. So dA ij is just d f0 a dx and dxj. So this is the contribution from the integral over dx, and then integration over the Grassmann variables gives this Pfeffern, and then we have the familiar sum over non-empty graphs, IH to the power minus the order characteristic of the graph, automorphisms of gamma, and then the weight of the diagonal gamma. So here L A alpha beta is simply f alpha beta a, the quadratic, Grassmann quadratic part of the function f. And now the Gaussian integration over x will create the edges, say bosonic edges. Gaussian integration over c will create fermionic edges. So this graphs gamma, they will have edges of two types. And they will have vertices where these edges will come in. So the weights of these edges will be, the weight here is BA inverse I1 J1. The weight here will be L A inverse alpha 1 alpha 2, and then say K alpha 1 through alpha L. The weight here will be it's minus D K F alpha 1 alpha L of A over D I1 dx I2.
Excuse me, and you assume that you have no second derivative, mixed derivative, they are vanished as well, or
Yes, I'm sorry.
this?
Actually, this is, yes. So, this function is even in the sense that f alpha 1, alpha 2, alpha 3, and all these odd terms are different. So this L here is always even.
Okay, so that's an assumption on F.
That's an assumption, yes. Yes, otherwise we would have to deal with the vertices of odd parity with Grassmann vertices. So it's possible, but it's not necessary and it's messy. And it's not needed. Okay, so then the story is the same. But I forgot one important factor. Again, this is the diagram of gamma, and then there is minus 1 to the I of the diagram of gamma, where this I d gamma is the number of crossings of the fermionic edges. Okay, so here's the formula, and the reason why it's here because we are going to use it. So
And will you talk about fat graphs or this, the alternative formulation of these crossing numbers? I mean the local cyclic orientation. You've done it all in terms of maps to the plane.
yes, it can be done. Yes, so we'll talk about it. Let's not talk about it now because actually I want to give another version of this formula. So you see, this is given for the case when we have a flat frame. So when there's these fermionic operators are so-called neutral fermionic operators. So not operators, variables. So, but we have seen the formula where the determinants appear. So, and that's what actually we need. So let me erase something. Maybe I'll erase this part.
If you will speak about the log of this integral, or it's just nice fact that if you take the log, then the summation is over connected graphs only.
Yes, yes, of course. That's so let me write the final version of the integral that we need, and then I'll say about it. So just as before. So remember we have C and B variables, and then when you have two types of fermionic variables, this Gaussian integral is actually determined. It's not factor, and it's related to this identity for the factor. So now let's look at this integral. So here it's the integral over the manifold, supermanifold Mn2n. Coordinates here are x1, xn. Coordinates here c1, cm, c1 bar, cm bar. And let's assume that the function is, again, f0 x plus the next term will be alpha beta bar, and I will use the bar indices here to distinguish between c and c bar. Alpha beta bar x, c alpha c bar beta bar, plus, and this is a finite sum because, again, c alpha squared and c bar alpha squared is 0. So what we will have here is 1 over n factorial f alpha 1 alpha k. I think it's yes, so I'm going to put the k factorial squared. Beta 1 beta k bar x, and then c alpha c bar beta bar, plus and so on. So the number of c's is always equal to the number of c bars. Okay. So then the statement is that this integral is equal to, everything is the same except now we have the determinants, and then the difference is that in Feynman diagrams the fermionic edges will be oriented, say, from alpha to alpha bar, and here it will be alpha bar, and Bij is the same. Ba is ij is just bxi dj, and La alpha beta bar is simply f alpha beta bar a. And then here we have the edges coming in, and then the same number of fermionic edges going out. Okay, and here it's just number of crossings, it doesn't matter in which direction. And this is the formula that we need. So, again, the definition of the left side is first you integrate over c and c bar in the sense that you take top exterior power of this expression. The top exterior power is the function of x, and then you integrate this function of x with respect to the volume measure dx. And the statement is that assuming that there is a finitely many, same assumptions, finitely many simple critical points, then the asymptotical expansion is given by the sum of Feynman diagrams. Okay. So now I want to now let's look at the following. Suppose that gamma 1 is joint union with gamma 2. So let's suppose that gamma is joint union of gamma 1 with gamma 1 for some different graph gamma. Then the automorphism group of gamma will be equal to the number of elements, will be equal to twice the number of elements in the automorphism group of gamma 1, because
Square.
because
Twice squared.
And two.
twice square. Yes. Because you can permit them and you can do the automorphisms inside. So if you will use this observation and kind of explore it further, you will see that this sum and also in this case the weight factor just is simply the product of weight factors. So if you explore this, you will see that this is the sum over connected gamma, trivial, and then the same thing. So this was somewhat preliminary exercise. So now the real exercise. Any question about preliminary exercises? So now I want to return to this problem of writing the asymptotical expansion for the oscillatory integral when there is a Lie group acting on the manifold and when the critical points form critical orbits. And they are such that in the quotient space, critical orbits correspond to simple critical points. So, yeah.
It's just impossible to hear the lecture and
No,
on the camera. So therefore we just wait, it's fine.
Sorry.
No, but if there is a question, you know, it's
No, it was just, I was asking what the asymptotics, I wasn't here the other day, so I was just asking.
What is asymptotical equivalence means?
Yes.
Okay.
What it was precise, because it was not stated in the notes.
Yeah. Oh, yeah, that's right. So, Marcel explained. So it's a okay. So now we have the integral over n even x h dx. There is a group G acting on M, and all the assumptions that so both of them are compact. Critical points of F are sitting on orbits of G without stabilizers and so on. So now the idea is the following. We want to write this integral as the integral over M mod G, but M mod G is a singular space, and what I really want to find is the asymptotical expansion of this integral as h goes to 0. So in some sense, really all I need is the structure of this integral near the critical points. And in this, and so the idea is, rather than to, in any case, if you want to compute something on M mod G, you always have to choose a model of M mod G as a cross section. Or you can use invariant functions, but that can be quite complicated. So a very natural idea is to choose a cross section and to write this integral as the integral of a cross section through the set of orbits. And when you have a compact group acting on a compact manifold, there could be no good cross sections very easily. So, but remember, what we really need is the asymptotical expansion. So we need a cross section that is really sort of intersecting transversely orbits in the vicinity of these critical orbits. All we need is how it behaves outside of these orbits. It's not that important for the asymptotical expansion. So then, first step is to write this integral in terms of the integral over the cross section, and then we will use the formula that I'm raising to write it in terms of Feynman diagrams. So let's assume that S is given by some equations. I equals 1 to n. N is the dimension of G. And so this is the cross section S, and then it's transversive to the G orbits. So let's choose a basis EA 1 to n in the Lie algebra G. Lie group acts on M, so we have a mapping of G to the vector fields on M. And because we assume that S is a cross section, this matrix, so locally EA acts as some kind of first order differential operator. So let's denote this matrix as MAP. So because of our assumption that it's a cross section through the orbits, the determinant of L is non-zero. And I also assume that the action is without stabilizers. So then the first statement is the following: integral over M e fx over h dx is equal to G integral over the space L exponent f, then the determinant of x, and then the delta distribution that localizes the integral. So I should be reading. So this is simply the way how we define S. Is the product delta distribution that is supported on S. So that's the first statement, so we'll prove it, as well as the second statement. And the second statement is that, so let's say this is 1, 2 is that this is also equal to G integral E with a factor H to the n. I'll call it Fp x C bar C over H and lambda dx dc bar dc d lambda, where this is equal to f of x plus sum over a from 1 to n lambda a p. Before it's too late, let's change this to. I already used yes. Oh. Minus IH sum over A B C bar upper index C lower. Now notice that here we're integrating over M cross G. So this is the even part, and then G cross G dual, this is the odd part. So it's a super manifold of dimension D is the dimension of M plus N to M. Well, it's getting late, so I think it's just the following. I will show, it's a very easy step to go from 1 to 2. It's slightly more involved step number 1. So if we'll have time, we'll do it today, but otherwise I'll just start next lecture with the proof of the first step. So 1 to 2 is obvious. It's when you have delta, such delta distribution, delta lambda or delta phi, you can write as the, sort of in terms of Fourier transform, it's the integral over Rn e to the I sum over a from 1 to n lambda a p a g lambda. And then we want to have I over h in the denominator, so for this I should introduce h here. Correct? Yes, so it should be h3 minus. That's the first thing, and then the second thing is when you have the determinant of x of L, then you write the determinant in terms of the Grassmann integral as e to the, and for some reasons it should have been minus. I just, so it's AB CA CB. Oh no, that's correct. So this is DC bar DC, but then this is exactly e to the I over h minus IH, that part, C bar LC, dC bar dC. So in some sense this is just a convenient way to write this integral. And convenient in the sense that this is rather singular thing. You have delta functions which are localizing this integral on S, and in this case you're integrating not over this smaller space but sort of over the bigger space, but the idea is very similar to using Lagrange multipliers when you find the extreme of the function with the generally critical points. Okay, so this is the main formula. So you say this one, and the main formula in the sense that if you look at the critical points of this function, this is really the function with the Lagrange multipliers lambda. So the critical points of f, they are not isolated. They have these degenerate directions along the orbits. But the critical points of this function, they are isolated. But they are isolated in the bigger space, in the space of x and lambda. So now if you want to find the expression for this integral in terms of Feynman diagrams, you can simply use this this form of the integral where the critical points are non-degenerate to write the asymptotical expansion. The problem with this, well, it's not a problem, but it's a feature of this asymptotical expansion will be the following. This expansion in Feynman diagrams will depend explicitly on the choice of the cross-section. In gauge theory, this choice of cross-section is called gauge condition. So physicists in papers on quantum field theory on gauge systems, they discuss the dependence or the independence of something on the gauge condition. So it translates to the fact that we know that this integral doesn't depend on the choice of phi. We started with the integral that doesn't depend on it. So the asymptotical expansion should not depend on the choice of phi. But if you just look at the formula, they do depend explicitly on the choice of phi. So one should prove then at the end that actually this expansion is gauge independent. That say in particular, if you will write this thing as a sum of Feynman diagrams, it's a computation that shows that if you will do some small variation of phi, then this variation is 0. So that's okay. So this is what we will discuss next time. I think now I should stop. So next time I will derive this formula, and I will write the asymptotical expansion of this integral in terms of Feynman diagram, and then an interesting feature of this expansion is that it involves these fermionic degrees of freedom, and in particular the appearance of this Fadeev-Popov action. So then we will see that, and that's the observation of Becquerel, Stara, and Tiffin, that there is a certain algebraical meaning in this expression. It's not just repackaging of this integral. This is a cocycle in the Chevalier complex for the Lie algebra G with coefficients in functions on M. And the homology class of this cocycle is given by this function f. So it's a very specific choice of co-cycle for this cohomology class. So, and then we'll see that there is an algebraic formulation of this statement in terms of Chevalier complex. And in this algebraic formulation, it's clear that this is just one possibility of choose such type. In principle, you can choose any complex with the same cohomology spaces with the invariant functions on M, G invariant functions on M. And there is no reason why there would be no other Feynman diagrams describing the asymptotical expansion in some completely different terms. But then all of them give the same answer because all of these complexes are quasi-isomorphic. They have the same cohomologies. And actually this integral is it's the integral effectively over M mod G, which means that it is something that's based on the cohomologies of these spaces. But then you can write a model for this integral in terms of any quasi-isomorphic complex. And that's what, algebraically, that's what Fadeev-Popov is. It's a very specific choice of this complex. So this is the plan to come on.
The instruction over is not Morse function.
Why it's not Morse?
Morse, because it's not Morse, but the general critical point for
No, you don't have to. It's a Morse function M cross G on this space.
And what is
So the second derivative will be of this form. But the determinant is still non-zero. You know, there are, yes, so this will be x and the derivative is then the random derivative, this is x and this is x.
Är det därför det är viktigt att visa aggregation?
Well, they are on the outside. I mean,
Good point.
And it's really, it's sort of actually interesting to hear the way you presented the arguments, because that's the way it's done for path integrals. Because it should have been a corollary of this theorem that no matter how we choose the slice, if it's truly an asymptotic expansion of this quantity, when we've summed over all diagrams, the quantities will be determined by what we start with expanding. So you know, that would be a corollary. But if we do not have a definition of this, like in path integrals, we will have to rely on proving that this is, you know, that this is invariant under the slice.
Yes, exactly. So the whole discussion of the gauge independence comes at the moment when we replace the definition of the integral by the formal power series with the same ingredients. And then we have to prove that it's gauge independent, because then we don't know whether it's an asymptotical expansion of some integral. And that's what sort of this problem of gauge independence and gauge theories is. Because there is no path integral, yes, you're right. Yes.